Hello everyone, and thanks for tuning in to this Aerospace Testing International and United Electronics Industries webinar. It's called The Language of Avionics, Effectively Transmit, Process and Monitor Avionics Data. The format of today's session is quite straightforward. We'll have a short presentation from Eric Gothart, followed by a Q&A session. Please do post any questions that you have during the presentation for Eric to answer, and his colleague Phil Zavitas, who is also joining us. That will enable us to get through as many of the questions as possible after the presentation. So I'll just do brief introductions for Eric and Phil. Eric has designed, managed and implemented many products that collect real-world data in the aerospace, energy and defense industries that have enabled his customers to build smart systems that are reliable, flexible and rugged. He has more than 30 years of experience in industry-wide hardware, software and I/O application solutions. Then also we have Phil. Phil is an expert in developing and launching embedded systems with over 15 years of experience. He's worked at Wind River Systems, Green Hill Software and QNX Software, and possesses an extensive knowledge of a variety of embedded hardware and software technologies within the aerospace, military, transportation, energy, and many more industries. Hi, Eric. Hi, Phil.
Good morning.
Good morning.
And thank you.
Good stuff. Thanks for joining us today, and thanks to everybody for tuning in now. So over to you, Eric. Looking forward to your presentation.
Yeah, thanks. And I hope everyone is staying safe and healthy in these unprecedented times. Shall we jump right in?
Right.
So let's look into this Airbus 350 cockpit. There are various instruments and panels. ARINC-825 is used to communicate with the overhead panel. ARINC-429 is used for radio control. ARINC-664 is for most of the other instruments, with ARINC-429 providing a backup at lower bandwidth. ARINC-429, MIL Standard 1553, ARINC-825, ARINC-664, AFDX, ARINC-708, CSDB, ASCB. There are so many, and all these interfaces have one thing in common. They are used to move messages across a bus to acquire data and control avionic instruments. Testing, verifying, simulating, and controlling avionic buses present many challenges. Message timing, message error checking, message content, message synchronization, bus timing, bus speed, and more. We will be reviewing these methods and more to control and verify avionic equipment. So let's get started with ARINC-429. It's an old interface used on pretty much every civilian and transport aircraft today. Designed in the 1970s, it has become the standard local area network for commercial and transport aircraft. Various systems such as communications, guidance, altitude, attitude reference, flight management, and more all need to work together to accomplish a successful flight. Thus, ARINC-429 was born. Communication protocols for ARINC-429 are derived from the technology in the instruments themselves. Discrete instruments produce discrete data. The standalone instruments of the 1970s needed wires to connect them, either a transmitter or a receiver, one direction only, typically one transmitter to many receivers. The goal of 429 is to set standard messages or labels on a common bus so that instruments from different manufacturers can be interchangeable. Here is the 429 message format. The label indicates the type of equipment sending the message. Label 203, for instance, might be altitude. Thus, all altimeter manufacturers would have the label 203 in their messages. You can also see bits for data, parity, SSM, and SDI. You will find many avionics suites have their own messages and labels. True testing of avionic systems occur after the known good cases are run. If everything works, that's great, but what does your system do when things are not right? You need the ability to change any field in the 429 message so that it is not correct. You need to be able to force a parity error. have an out-of-bounds data for a particular label, change the SDI or SSM at will. All this leads to fully testing a deployed system or causing failures in a simulation where people can learn to recover from them. The 429 specification asks that the equipment transmit at one of two rates, 10 to 14.5 kilohertz and 100 kilohertz. However, equipment may vary from these rates. The specification states plus or minus 1%. The design verification process needs to test these limits and more. You need a tool to get the job done in the real world. What are your test limits? You need the ability for custom transmission rates, perhaps from 10K to 200 kilobits per second. All this is needed for the design verification process of your avionics. So what happens when the 429 data does not arrive? Yes, perhaps an inop or an inoperable. Typical update frame rates of ARINC-429 devices are 25 milliseconds, 40 milliseconds, and 66 milliseconds. Avionics usually show inop or inoperable when 2 consecutive frames are missing. For example, when the updating thread is delayed for more than 2 periods. Can your software algorithm keep up with all the labels and not miss timing on any one of them? What else is your software tasked to accomplish? Is there enough CPU bandwidth? I bet you there's a better way. If you need to send a message, there are a couple methods you can use. A first in, first out buffer or FIFO-based method, where the command is simply transmitted when you call the FIFO's API, as shown here on the left. Or you can set up an advanced scheduler that allows for hardware to find message transmissions. Options for these can include master and slave entries, so one or more slave messages are sent only when the master messages is sent. Messages can be transmitted at many different frequencies on a periodic basis. Message can be sent as a reaction to another message being transmitted. The second message can be delayed by a variable number of clock ticks. A notification to the application when a particular command was sent or received. Messages can be sent once or periodically. Real-world testing requires a flexible, capable scheduler. And of course, this should be accomplished on the FPGA for microsecond timing with no latency and no load on the application software. Different scenarios require different solutions. We had a customer who needed to send a synchronized pulse upon the receipt of a GPS label 270. While this can be accomplished in software, the turnaround time coupled with the uncertainty of network latency made the solution not very desirable. We adapted our hardware-based system for microsecond response to any label. That is precise synchronization indeed. Many systems require bus conversion, bridging, or data concentrators. All need precise timing. Again, software may be a solution, but hardware-based FPGA systems are far superior. Shall we move on to MIL Standard 1553? MIL Standard 1553 was developed for military aircraft and thus had to be 100% reliable. It was developed in 1973 and first deployed on the F-16, and as seen by this partial list, was adopted for many, many aircraft going forward. It was so reliable, other types of craft started using it. To attest to the certainty of the design, the current standard is from 1978. It's more than 40 years old. Does anyone know where 1553 is used the most? Where the most 1553 buses are? Actually, it's on the International Space Station. It's used for everything there. It's even used on the toilet, believe it or not. The goal of 1553 is to move up to 32 16-bit words on the bus, but it's as simple as that. A military aircraft is run by a series of 16-bit words. So why is it so popular? It is simple, deterministic, and reliable. So what are some of the components of a 1553 system, and how do you control them? The bus controller would be the mission computer. A remote terminal may be a missile launcher, which would make each missile a subaddress. Or a remote terminal may be an instrument supplying the mission computer with airspeed data, for example. The bus controller is the only component that can initiate traffic on the bus. If the bus controller needs information from an instrument, it sends a command. If the bus controller has to give information to a missile, for instance, it sends a command and data. A FIFO-based bus controller is excellent at targeted testing of many RT and SAs. But when you need to send commands to many RTSAs at different frequencies to emulate a real aircraft, the major minor frame scheduler is the solution. The bus monitor is an option to be used or not, and simply allows you to view or record any or all traffic on the 1553 bus. It cannot interfere with this traffic in any way. Each 1553 system has two sides on the physical bus for redundancy in case one side becomes disconnected or disabled through an aerial engagement or really for any other reason. Messages on the bus can take several forms. A BC to RT command sends data to a remote terminal subaddress. For instance, the mission computer may have to send a firing command to a missile. An RT to BC command asks the RTSA to send data to the mission computer. For instance, that might be airspeed or temperature data that the mission computer needs. Combining the two creates an RT to RT command, where one RT sends data to another RT. Mode commands are special commands that change the condition of the system, like resetting a remote terminal, synchronizing time across terminals, or dropping a faulty bus. And finally, status, or the status word. When messages are sent, status words are the first replies. The RT sends the bus controller a status word when it receives a command. Clear status is the most desirable, of course, indicating there were no issues. But if the RT has to tell the BC that there was an issue with the command, this is the method. We mentioned that 1553 is reliable. The status word is a key piece of this reliability, for if it was not there, how would the BC know if the RT had issues with the command? Each bit in this important status word has a meaning. Was there a message error, ME, or is the RT busy? The bits in the status word indicate whether a command has been properly received as well as the status of the RT itself. To stress your system, you should have the ability to force errors in these bits to see how the system behaves. We just discussed in the previous slide sending commands and receiving status messages. The picture here represents a 1553 bus upon which the messages travel. In a 1553 system, standards are expected to be met. Timing must be adhered to. If data arrives early or late, it's an issue. If too many or too few words arrive, this is another issue. A 1553 command indicates the number of words that the RT should send or the number of words that the BC has sent. If more or less than this is specified, it is an error. When testing a system, if everything is working, you feel confident in deploying such a system. But if testing did not involve injecting errors to see how the design handled them, you might get a surprise a few months later. You need to inject errors to prove out your design so that you can be confident that your design will handle real-world issues once it's deployed. In simulators and maintenance trainers, error injection is used to simulate a fault on the 1553 bus and help the person at the controls learn to deal with the issue. Better to do it there than up in the air. As with 429, we found that there are a couple different methods to transfer data or messages over the 1553 bus. A FIFO, or first in, first out based buffer, and a hardware-based scheduler. The FIFO method on the left simply sends a message when you call it. It's as simple as that. For real-world interactions, you also need the ability to insert a delay between sending your next command. The best way to handle the transmission and delay is in an FPGA. Being able to send commands is nice, but being able to control the precise timing between them is even better. In a real aircraft, instruments and armaments are not run on at the same rates. To accomplish the very real task of flying an aircraft, taking in instrument data and firing ordnance, a scheduler has to be able to send commands at varying frequencies to each RTSA. A major minor frame scheduler can do this and more. Sometimes a major minor frame scheduler is overkill, but the precise timing is still needed. System test and validation can be accomplished with an easy-to-use hardware-based FIFO scheduler. So how would you change the data in an RT message fast enough to keep up with the 1553 timing requirements? Typical message delay is less than 200 microseconds, subject to the host latency. Perhaps use a hardware-based lookup table. A lookup table is a mechanism to replace the data that will be transmitted by an RTSA with pre-stored data upon receiving a command. This command, which is on the same RTSA, is analyzed to match a programmed size and pattern. For example, a signal to take the data from the lookup table and send it to the next transmit command. This allows for hardware-timed custom messages to be sent. Simulation and test are dynamic environments that need a flexible system. Being able to change the data in hardware without an external application involved is real-time gold. Doing it in firmware is much faster because it doesn't depend on network and host timing to change data. We have used this feature with munition interfaces. One customer required a pulse to be sent out of the system based on a pre-programmed RTSA command being issued. Non-1553 equipment can now be synchronized to the message-based system. Another example is a digital pulse driving the avionics. The signal triggers the FIFO-based bus controller to send the data, synchronizing the data collection in the entire system. All done on the FPGA, assuring precise timing and synchronization. So you have an LRU that needs to be tested. Using schedulers, you can send a series of messages to exercise 100% of your RTSAs. You can change the timing between the messages to see how RTSAs respond to the changes, whether you are simulating or testing devices. You can see the timing in detail using the bus monitor as the timing between messages and data words is brought out for inspection, and inject a wide variety of errors in the bus traffic and in the status word to stress the system before it is deployed. This represents a typical simulate or stimulate based block diagram. Hardware can be used to generate traffic, respond to traffic, or modify traffic. Real or virtual hardware can be used. Shall we jump into ARINC-708? It uses the 1553 infrastructure. ARINC-708 is typically used for weather radar. I'm not sure if that's me, but if somebody could mute. Thank you. ARINC-708 is typically used for weather radar and enhanced ground proximity warning system applications. It uses the 1553 bus as the transport mechanism. However, the messages are a completely different structure. Data is allowed to travel both on side A and side B simultaneously and at a higher rate than standard 1553. Data frames are 1600 bits long, with the header portion of the frame consisting of parameters such as range, tilt, gain, status, and stuff like that. The data portion is organized into 512 range bits per scan angle value. Each range bit contains a color value that indicates the intensity of that position. WXPD brings much better graphics to the radar display unit since it contains fonts and label information. It increases the data size by 2,000 bytes. A pilot needs to quickly understand a situation while multitasking and flying an aircraft. WXPD is an attempt to display a clear picture of this complicated information. As we have mentioned, stress testing a system by injecting errors is critical to the product reliability or the simulation's effectiveness as a real-world trainer. ARINC-708 is no different. You need to be able to change the major attributes at any time. The frame size can be different than the expected defaults of 1600 for 708 and 2000 for WXPD. You can change the timing between frames to see how the LRU behaves when latencies are introduced. You can change the timing of the edge of a bit to be out of specification. You can also change whether a bit starts on the leading or following edge of the pulse. All this helps stress the systems for reliable LRUs. Many older avionics systems are serial, RS-222, 422, or 232 based. Collins Standard Data Bus, now Commercial Standard Data Bus, is one. Avionics Standard Communication Bus, or ASCB, is another. The same challenges are present. You want to test the limits to verify functionality. Typically, you need to be able to have programmable clocks for character delay and frame delay. Baud rates, packet sizes all need to be controllable. One challenge we have with older avionics is that they have a slower CPU which can't process serial streams at the full baud rate. Inserting delays between characters allows the application to talk to those devices. The need for algorithms to maintain the connection to the avionics points to the need for a hardware-based scheduler, similar to what is needed for 429 and 1553. So how do you test now? Most people are using 100% physical iron birds in their software and hardware integration labs. They are typically very expensive and depend upon having the different avionics and sensors in every bench. One way to avoid these difficulties can be a virtual testing approach. It's a promising solution that has already demonstrated its benefits in other industries such as cell phones. Another method is hybrid testing. Some hardware in two different places connected over Ethernet. This virtual environment uses IP or UDP to connect virtual and real-world hardware to accomplish system testing in an efficient and cost-effective manner. If the hardware is not present, it can be simulated. The simulation can run remotely with the simulation communicating with the hardware via IP or UDP messages. Real hardware can be switched in at any time, or even distributed in many different locations. So now I'd like to introduce a concept called VISTAS. The idea of VISTAS is to create a protocol for testing avionics systems. Very often, a particular avionics device can't be tested alone. It requires other parts of the avionics suite to be present and deliver information, hence the iron bird. To accomplish that, VISTAS allows easy substitution of missing parts to be emulated using hardware such as UEI's Avionics Interfaces. Additionally, it is possible to create a virtual bridge between the test setup and an avionics device, which could be located in some other remote location. To do that, one set of UEI Avionics interfaces talks to the device and another set talks to the test bench. Two sets are connected via local or global TCP/IP network. Although the virtual link between the emulation and the emulation hardware could have a latency or jitter, if it's set up correctly, the emulation hardware can use the hardware schedulers we discussed to solve those problems. Avionics are typically more sensitive to schedule than message content. Stale messages may be okay for one cycle. This is a perfect match for hardware-based message handling. Using IP or UDP to connect virtual and real-world hardware accomplishes the system test in an efficient and cost-effective manner. If the hardware is not present, it can be simulated. The simulation can be run remotely with the simulation communicating with the hardware via IP or UDP messages. Real hardware can be switched in at any time. You are no longer limited to the signal's attenuation due to the analog wiring. The equipment could be in different rooms or buildings at the same site. The equipment could be in different sites if transmission delay was acceptable. Or the equipment could even still be in the manufacturer's facilities, allowing early integration tests. VISTAS, or Virtual Inoperable Simulation for Tests of Avionics Systems, is in the Euro CAE working group currently. It promises to decrease the time it takes to verify avionics. Whether you are verifying your equipment with hardware and software testing or testing the entire system, the benefits include functional verification, anomaly investigation and debugging, fault tolerance, and even system limit testing. VISTAS is a shared standard among aircraft builders, avionics manufacturers, and test system providers. It is an ultralight protocol, a kind of hardware abstraction layer, giving you the capability to measure and replay the timing encountered on real equipment. This system has many benefits for the designer, validator, and integrator. VISTAS allows the distributed testing where the different components do not need to be co-located in the same building. Hybrid testing that mixes real and virtual components certainly helps early in the design and integration stages. As you progress further down the verification and validation cycle, VISTAS allows a quick swap between real equipment and virtual ones. All of this helps in earlier validation. Models can be shared during the entire development cycle. It doesn't matter if virtual or real hardware is being used. And of course, there's much wiring, reduction, and simplification. So where can you find out more information? Well, it is the EuroCAE ED-247 is the topic. And it is currently in version 2 point something right now. And there's an open source library set as seen on the screen at www.polarsys.org, projects and polarsys.libims, where you can see some of the code set. Well, that's all I have for today. Thank you for your interest. Please call or email with your questions or interests in UEI's integrated avionics solutions. You can reach me at eric@ueidac.com or at 508-921-4567. I think we've got time for a few questions.
Yeah, thanks, Eric. Yeah, we do have. So if anyone's got any questions on that, I thought that was a great, just most straightforward run through of this area that I've ever encountered. So thank you for that. And VISTAS is certainly seems like an important innovation within the sector. Am I right? Is it a big step forward?
I believe yes, that it is a big step forward. We're seeing many benefits with some of our partners over in Europe.
Great, and and how far is that standard's going to be throughout the whole industry? Right, that's going to benefit everyone.
That is certainly the idea, from the avionics manufacturers to the airframers to the system integrators.
Okay, great stuff. Is Phil on the line now as well, or is he?
I am.
Great. Okay, Phil. Thanks for joining us. So I've just got a few questions here to get the ball rolling, as it were. Interesting to hear there about ARINC. Can you convert ARINC 429 to 1553? Is that something that's possible?
Yes, we have I/O boards for 429 and 1553, and your application can read from 429 and put it on the 1553 bus, or vice versa.
Okay, that's great. So, and what about analog inputs? Can you take those and put it on a 429 bus, for instance?
Absolutely, we have a wide variety of analog input boards, and you select the one for your application. And the application running can read from the analog input and put it on the 1553 or 429 bus.
Okay, fantastic. And you're an embedded systems guy. I mean, and do you have a fully standalone embedded controller that's available for this stuff?
Yes, our hardware runs in two modes, and one is a standalone, fully embedded mode running a real-time Linux or VxWorks. And the same application can run on the hardware when it's in our distributed networking mode. And the distributed networking mode relies on the application running on a PC. So you have both worlds, fully standalone embedded or a networked system.
Okay, right. Thank you for that, Chris. We've got a few in from the audience here, so we'll just run through these. I've got one here from Chris Earl, who wants to know. This was quite early on in the presentation, that if there are two buses, then how can one determine which bus has the valid data if the data received is different between the two buses? I don't know who wants to take that one.
Well, in 1553, each RTSA is hooked to two different buses, bus A and bus B, for redundancy. So the bus controller will send a message on bus A, and if it does not receive a reply, it will send the same message on bus B. So the data should be the same. It's just a question of which bus is it coming over.
Okay, great. I hope that answers your question there, Chris. I've got one here from Irene Lau. She's asking, why would you want to use 429 versus 1553?
429 are direct connections between equipment, and it's an older standard. The military aircraft and the ISS use the 1553 bus so that you can have 900 devices on the bus and all be talked to in the same protocol without direct connections between the 900 devices.
Okay, fantastic. And I guess you've got that kind of pedigree of the decades of its usage backing it up for its reliability still.
Right, and we've found that ARINC-429 typically is for commercial versus 1553 is for more the military type aircraft.
Okay, great. Well, that's all the submitted questions that we have from the audience right now. I mean, if anyone else has anything that they want to ask our two experts here, now's the time, or forever hold your peace. Great. Okay. Well, if anybody wants to follow up, there's Eric's details on the screen there, and I'm sure we could get questions to Phil as well. So I don't know if you guys want to sum up or finish up by saying anything, Eric or Phil. Eric, do you want to go first?
Sure. I just want to thank everybody for their time, and I wish you luck in the pandemic as well as with your avionic projects.
Great. Thanks for your time, Eric. Phil, is there anything you'd like to add, or?
Well, thank you for attending, and if you want any more information, please reach out.
Great, good stuff. And this webinar will be available. You'll get a link through within the next 24 hours. And then it will be on our website, aerospace-testing-international.com, to view as well. So yeah, thanks for tuning in. My thanks to Eric and Phil for giving a great presentation and answering the questions. Oh, do you want to take this one, guys? Tim Shannon's suddenly had a burst of inspiration here. He wants to know about certification testing and conformity, which he says is normally done at a place of manufacture. So is it envisaged that VISTAS simulation across two locations will be acceptable to civil certification authorities?
That's a great question, and the answer is, we just moved it into published.
Yes, sorry.
And the answer is, I believe they're still working on that. I do know the biggest value add for VISTAS is the ability to share the simulation of the avionics piece of equipment early to any of the system integrators and the airframers so that they can determine how it works in their system without actually having the physical piece of hardware. And then you can then swap out the simulation with the real piece of equipment afterwards. So I do know that they're still working with the civil authorities to try and determine if it will be acceptable eventually. That's a great question.
Good stuff. Okay, thank you. Another late entry here from Jayantha KV. That seems like the audience doesn't want to let you guys escape quite yet. They would like to know what will be the standard protocol latency during protocol conversion, especially for Mills standard 1553 to Ethernet. Who does that make the most sense to?
Our head of engineering tends to have these hard numbers. I don't. It's very fast, and our systems have been deployed hundreds of times, if not, 1,000 times. So there is not enough latency to interfere with any application.
Okay.
That
great.
I've come across.
Good stuff. Okay. I hope that answers the question there. Right. So I guess this really is goodbye this time. So have a great day, everyone, and I hope to hear from you all soon. Cheers. Bye bye.
Thank you.